Right, tonight I'm going to be reviewing for your next exam. Okay, this is only a summary of the material, and I'll just present a few representative examples. Chapter 4, the study of chemical reactions. There won't be a lot. I'll talk about some of the main ideas. Draw that a little bit bigger. All right, here is a reaction profile diagram. Y-axis represents energy. The x-axis represents progress of reaction. Okay, this would represent the energy of the reactants. This is the energy of the products. And this difference is the change in energy. So this would be an exothermic reaction. Right, this distance represents the activation energy. We'll call it EA1. And since this is larger, this is the slower rate determining step. This represents a transition state. This would be an intermediate. This is the second transition state. And EA2. Right, the Hammond postulate says that species that are similar in energy are similar in structure. Okay, so what that means in terms of, this is the Hammond postulate. Okay, in the Hammond postulate, if a step is endothermic, for example, this first step, the transition state would more closely resemble the intermediate than it would the starting material. Okay, and that would be the same way for step 2. Okay, we also looked at free radicals and free radical chain reactions. I'll run through a simple free radical substitution. Okay, if we expose chlorine to heat or light, we have an initiation step. We use a single bar fishhook arrow to represent a single electron. This is initiation. Then we have a propagation step. We use cyclohexane here. Okay, that gives us a cyclohexyl radical and HCl. Okay, and then we have another propagation step. For example, and then termination steps result when two free radicals combine to form a covalent bond. Okay, so initiation, propagation, and termination. Okay, so one example of a termination step would be this. more substituted a free radical is, the more stable it is. Okay, so for example, this is a tertiary free radical. This would be more stable than a secondary free radical, say this one here. That is more stable than a primary. Something else that confers stability to free radicals is resonance. Okay, so if we have what is called an allylic free radical, okay, where the odd electron can be delocalized, this is very stabilizing as well. Okay, in chapter 5, we looked at the subject of stereochemistry, and we started out by talking about chirality. Chirality means handedness. So if an object or a molecule is chiral, then it has this property of handedness. Okay, things like gloves and shoes and chiral molecules. If something is achiral, that means it's not chiral. Chirality and optical activity go together. Chirality represents the structure. Optical activity is a property we measure in the laboratory. And as far as we know, there's an exact correspondence between chirality and optical activity. And everything that is not chiral is not optically active. Enantiomers are non-superimposable mirror images. Okay, and the key word there is non-superimposable mirror images. Okay, everything has a mirror image except a vampire. And what you want to look for is what is called a chirality center, or stereo center, or chiral center. The terms are used interchangeably. And what to look for there is 4 different atoms or groups attached to a carbon atom, although it could be other elements as well. Okay, 4 different groups attached. Okay, but mainly we're going to be talking about carbon. Okay, each time we add a chirality center to a molecule, we double the number of possible stereoisomers. Okay, so if we have n stereoisomers, or if we have n chiral centers, I should say, we would have 2 to the nth power stereoisomers. Okay, so if a molecule has 5 stereocenters, we would have 2 to the 5th power, or 32 possible stereoisomers. Okay, we distinguished stereoisomers using the R and S system. Okay, we go by atomic number, and we look at the 4 atoms that are immediately attached. Okay, so we have Sulfur is highest priority, that's atomic number 16. Okay, hydrogen is last. Okay, carbon, we have carbon and carbon, so we have a tie here. So we go out to the next one. Okay, the next one here is a hydrogen versus a carbon. So the butyl group here takes priority over the methyl. So it goes 1, 2, 3. The lowest group is back, and so this one is R. In a Fisher projection, chiral centers are represented as pairs of intersecting lines. Right, this is a compound called tartaric acid. And each chiral center is independent. We have 2 chiral centers. All right, so we prioritize. This is oxygen is 1. We've got carbon and carbon. Okay, next one is an oxygen. Okay, but then we can treat this like it's 3 oxygens. So the group up at the top takes priority. So that's 2, and then the group down at the bottom is third. Okay, so we go 1, 2, 3. Except by definition, horizontal groups are forward in a Fisher projection, vertical groups are back. And so for a Fisher projection, it's usually backwards. Okay, so while this looks like it is S, it's actually R because we're looking at it from the wrong direction. Okay, so this would be 2R. Okay, and then looking at the other chiral center, again, oxygen is 1. The carboxylic acid group is 2. The carbon with the alcohol is 3. So that's 1, 2, 3. Okay, that looks clockwise, but is actually backwards again. And so this is 2R3S. Right, this one is, even though it has chiral centers, it is optically inactive. It is achiral, and that is because it contains a plane of symmetry. And a plane of symmetry would negate chirality. And so this is called a meso, because it is an achiral diastereomer. Okay, to get a diastereomer of this, we would invert some of the chiral centers, but not all of them. Okay, so for example, okay, so these would be related as diastereomers. They are stereoisomers. The substituents are all on the same carbon numbers. Their three-dimensional shape is different. Okay, since we kept carbon number 2 the same, but we changed number 3, this one would be 2R, 3R. And for the enantiomer of this one, this one is now optically active, is chiral. The enantiomer would have the configuration 2S, 3S. We would invert both of the chiral centers. Okay, I'll have you draw structures and on the test. I'll have you draw structures. And in the name, if R or S is designated, I have to be able to tell if it is R or S. Okay, for example, if I said, okay, I want you to draw R, 3-bromo cyclopentane. Cyclopentene. Okay, that would not get full credit because I can't tell if that's R or S. Okay, so you would have to indicate that it's R. Okay, now if I were to do this, that goes 1, 2. Okay, the alkene takes priority over the CH2. 1, 2, 3. So that's actually going to be S. There is an easy fix for that. If you've drawn the wrong isomer, you can just switch any two groups. Okay, so there, I fixed it. And that's the R. Okay, same way with E and Z, which we'll talk about later. I have to be able to tell by looking at it that it is E or Z. Right, a racemic mixture is an equimolar mixture of two enantiomers, an exact 50-50 mixture of two enantiomers. Racemic mixture is optically inactive. We say it's achiral. In chapter 6, we looked at halogenated alkanes. We looked at naming them. The substituents. This is fluoro. Okay, note the spelling. Also, fluoro is not FL, it's just F. This is chloro, bromo, and iodo. All right, we looked at one type of substitution that was a little different from the others. It was a free radical substitution, and it was allylic bromination. Okay, so if we have an alkene such as this, and there's a special allylic brominating reagent. It's called NBS, which stands for N-bromo-6-enamide. This will go through the allylic free radical. Okay, this is the most stable free radical, and the reason is because of resonance. And so bromination will occur at the allylic position. Okay, it's actually a very unstable free radical to have it at the alkene position. And these positions, they're secondary, but they're they would produce a free radical which is not resonance stabilized, so it's less stable than the allylic radical. Right, mostly we looked at SN1 and SN2. We'll start off by looking at SN2. Okay, in the SN2 reaction, okay, here we have a primary alkyl halide. We have a strong base, strong nucleophile. This is what's called the substrate. Chloride is the leaving group. In the SM2, there's only one step. This comes in from the backside and kicks out the leaving group. Okay, so we would end up with an ether and chloride ion. Right, if the leaving group is on a chiral center, complete inversion occurs. In this case, it's not on a chiral center because we have two groups that are the same, namely hydrogens. Okay, we can make a variety of different compounds using the SN2 reaction. Okay, for example, I showed you we could make an ether, we could make an azide. Right, so this would come in from the backside, and it would bring about complete inversion. That would push this hydrogen forward. Order of reactivity for SN2 is methyl, primary, and then secondary. Tertiary substrates are not subject to SN2 because they're too crowded on the backside, so the nucleophile can't attack. Right, protic solvents include those that can donate and accept hydrogen bonds. Okay, these would include water, alcohols, carboxylic acids, okay, such as acetic acid. Liquid ammonia could also be a protic solvent. Okay, so notice these all have OH and this has an NH. Okay, aprotic solvents can accept hydrogen bonds, but they can't donate them. Examples would be acetone, ethyl ether, or diethyl ether as it's sometimes called. This is called DMSO, dimethyl sulfoxide. This one's called DMF, dimethyl formamide. Okay, so these are examples of aprotic solvents. SN2 reactions will proceed faster in aprotic solvents than in protic solvents. You can still do many of them in protic solvents. Since the nucleophile, okay, and this actually only applies if the nucleophile has a negative charge. Okay, because the aprotic solvent will not solvate the anion, it's the cation. SN1. Okay, this is a first order reaction. This occurs in 2 steps or 3 steps, as in the case of our lab. We'll be making terphenyl chloride. In this case, OH is a poor leaving group, and so we need to protonate the oxygen first. Slow rate determining step is what we call heterolysis, where water leaves. Get this carbocation, this is the slow rate determining step, and then chloride comes in. Okay, we always draw negative to positive. Okay, this will give us terphenyl chloride, or 2-chloro, 2-methyl propane. The SN1 actually needs a protic solvent and needs to be able to separate both the anion and cation from each other and solvate them. The SN2 requires a strong nucleophile. The SN1, you can use a weak nucleophile, okay, like alcohols or water. The SN1 is first order kinetically. It depends just on that heterolysis. The rate depends only on that heterolysis step. Okay, the order of reactivity for SN1 is tertiary and then secondary. Okay, primary carbocation is won't go by SN1 because a primary and a methyl carbocation are too unstable. All right, in chapter 7, we looked at alkenes. Alkenes will be designated by the suffix ene. Alkenes, the alkene group takes priority over alkyl groups, such as these methyls, and over halogens. Okay, we have 5 carbons. This is pent, and it would be pent 1-ene. And it would be 4,4-dimethyl. If a ring contains a double bond, 1 double bond, and nothing higher priority than an alkene group, such as an alcohol or a ketone or something like that, the alkene group is assumed to be between carbons 1 and 2. Okay, so this would be cycloheptene. You could say cyclohep-1-ene, although it's not necessary. And it's understood the double bond is between 1 and 2, so this is 3,4-diethyl. Cycloheptene. Right, if a molecule contains more than one double bond, it would be a diene or triene or tetraene. In this case, this would be hexa, and it would be 1,3,5 triene. Okay. 3 double bonds, triene. Okay, we also looked at the E and Z, and this uses the same rules that the R and S uses, except we only compare substituents 2 at a time. Okay, so we compare the first atom, which is a carbon, they're the same. So we go to the next one. Okay, it's an oxygen, then a double bond would imply 2 oxygens, or at least for purposes of the rules, 2 oxygens. Okay, so the ketone takes priority over the alcohol. This is number 1. On this side, we have a carbon and a carbon. Nitrogen is higher priority than carbon, so this is number 1. These are opposites, so this would be E. As soon as we find a difference, we stop. So we compare the first one, and then we compare the second one, and the third, and so on until we find a difference. Okay, not every alkene will exhibit E or Z. Stereochemistry. Okay, for example, this were also a nitridyl group. Okay, this would be neither E nor Z. Okay, for smaller rings, the double bond within the ring has to be cis. The largest, or the smallest ring, I should say, that could accommodate a double bond, the trans double bond, is an 8-membered ring. Okay, this brings us to something called Brett's rule. Brett's rule says that for a bridge bicyclic compound, you cannot have a double bond at the bridgehead unless one of the rings has at least 8 carbons. Okay, a bridge bicyclic compound would have carbons at all 3 of the bridges. Okay, so this is a small bicyclic system. Okay, we cannot have a double bond here. Okay, that's actually not even possible. Okay, this is okay because that's not at the bridgehead and it's a cis double bond. Okay, next we'll look at elimination. And the 3 main types of elimination are dehydrohalogenation, that's where we remove a hydrogen and a halogen. Okay, this could be E1 or E2. Dehalogenation. That's removal of 2 halogens from adjacent carbons. Okay, this is E2. And then we have dehydration. And that's removal of H and OH from adjacent carbons. Right, these elimination, and this is E1. All right, so these elimination reactions are going to produce an alkene. Okay, unlike substitution, which can produce a variety of different functional groups. All right, let's look at E1 first. Okay, this actually competes with SN1. Starts out with the heterolysis step. Again, like SN1, this uses a weak base. Water is also the solvent. And then water comes along and removes a beta hydrogen. Okay, not this hydrogen here. Okay, but one on the next carbon over. And this will produce an alkene. Okay, so under these conditions, we could get a mixture of substitution and elimination. We could also get the alcohol. If we do it at higher temperature, that's more likely to favor the alkene. Okay, this is a first order reaction. This is the slow step, the heterolysis. It's unimolecular, that's where the 1 comes from. And this does require a polar solvent, okay, just like the SN1. At a higher temperature, it's going to favor elimination over substitution. Okay, E2 takes place in all one step. So in the E2, we need a strong base. Base takes the beta hydrogen, we form the double bond, we kick out the leaving group all in one step. Okay, one other big difference between the E1 and E2, besides the need for a strong base, is there are strict stereochemical requirements for the hydrogen and the halogen. The hydrogen and halogen have to be anti to each other. They have to be 180 degrees apart for the E2 to happen. Okay, it doesn't matter with the E1. In both the E2 and the E1, if there's more than one alkene that can be formed, we can predict the major product using Zaitsev's rule. Zaitsev's rule says that the more stable alkene, the more substituted alkene will be formed as the major product. This applies to both E1 and E2. The order of substrate reactivity for the E1 is tertiary and then secondary. Primary won't go E1 because that would form an unstable primary carbocation. E2 also goes in this order.